this computer. Cool. Hi, everybody. Welcome to week 3 of our general body meeting for Drexel AI. It is July 6th, 2021. I hope everyone had for those who celebrated, a good holiday over the past weekend. And today we're going to talk about our project, and hopefully we can get closer to actually implementing it and work on the formalization of it. I think it's important when you start a project to rigorously define what exactly you're going to do. I'll probably draw some stuff in PowerPoint, and we'll start a paper as well. And I'll just get all the foundation laid so that when we want to start implementing it in Python and running some tests, we'll be able to do that. So for those who haven't worked with Drexel AI before, we use Overleaf because it's an easy way to share files, share LaTeX documents, and we make all of our papers in LaTeX. And I want to copy one of these. Here's a paper that we didn't exactly do, didn't take anywhere from spring term, but we will copy it so that we can use it. And also we manage all of our code on GitHub. We're going to make a new repository, and we're going to name it sparse time series. I didn't spell forecasting wrong. There we go. Cool. Okay. We get public, readme, get ignore, license, Python. Okay. And this is where we're going to share all of our documents relating to code. And I'm just getting it set up, but I know I'm jumping around here because we have there's a lot of different parts to the project. So I wonder if I can copy this. First off, how's everyone doing? Do you have any comments about, I guess, the project? If anyone thought about it, we're going to get deeper into it today, but.
What's the project about? I didn't attend the last week's meeting.
Oh, yeah. So as a review, right, it was inspired by something you actually reminded me about. You have XY axis. This is some signal. S of t, some time. And we have some time series. I think we decided on doing like ECG signals. So just drawing a little waveform. It's more or less periodic. Actually, it should be more periodic, but my drawing is just really terrible. Anyway, so the idea is that, right, if you only have this data, you want to be able to predict. So if you have n time points, you want to predict. It's very easy to predict the next time point. And this is something that Dr. Kim told us about. So if you take random segments of the data, random regions, n data points from S of t, and you predict the n plus first data point, you can predict that with pretty high accuracy. But if you have n data points here, and as Alicia told us last time, that is I think it's a single step time series prediction. But what people are mostly concerned with is multi-step time series forecasting. So like this is like n, and this red dot's the n plus first time point. We are concerned with predicting the next m time points here. And that's a multi-step time series prediction. And that's arguably much more difficult, because you could imagine that if you have a window n long and you slide it to the right this way, eventually you're going to start using your predicted m, the predicted red values in m, to predict the next values. So, and then what will happen is, or what might happen is that the errors from these predictions will sum and your signal will diverge, and it won't look like what you expect it to look like. So you might get some, you might have the red diverge away from the signal, and it's not exactly intuitive how you could determine whether M is close or far from what it should have been predicted as. So a solution to that is to look at your first n time points in S and create a sparse representation using something known as sparse coding. Sparse coding is also called dictionary learning, and you basically learn a dictionary of atoms, and those atoms are like patches of features that in combination, in linear combination, they can represent it can represent an intelligible signal. So for instance, if we're dealing with, I lost my pointer, I lost my, okay. For example, we might find a dictionary element that is this. I think this is like an S wave in ECG. Or you might find a dictionary element that is the QRS. That is not the S wave. You might find a dictionary element that is QRS, or that contains this region right here. And I'm sorry, I lost my, I'm gonna stop sharing, I'm gonna reshare. Does anybody have any questions with the setup? Okay, it's back.
So you're assuming you're never updating, like you're not doing a rolling window prediction?
You are doing a rolling window prediction where you're always gonna predict, you wanna be able to predict M time points in the future, and in order to do that, you're gonna always predict the N plus first point, but you wanna be able to use, like in N, you don't wanna assume that the points in N aren't predictions.
Sorry, say that again.
You're not.
So the way you described it seemed like you wouldn't know if it was diverging, right? But
no,
as
you wouldn't.
time goes on, you would start to observe whether those predicted points match the real ones.
Yeah.
So I guess maybe can you clarify what?
Yeah, I can. Okay. So I guess the idea is if you wanted to predict M time points in the future, only using the N time, if you wanted to predict N points in the future, only using N, and it wasn't rolling, then you wouldn't be able to compare it to a signal. And the solution going around to get around that is to compare your predictions to a sparse representation of your N points in S. And you can do that in a generative way where you might have, this might be this might be in the first generation, this might be one, we'll call it one, I don't know, one child, one prediction, but you also might have another prediction, that's this yellow one, diverges in the opposite manner. And then you might have, the blue one that is actually the closest to what you'd expect. And the idea is that if you do, I don't know, like K predictions each generation, you can get some score function that compares all K of these to the sparse representation of your first N time points. And then the best ones, the highest scoring ones, the ones that match the sparse representation the best, would be used in subsequent generations. And that's a way to kind of get around the summing nature of the errors from a prediction. Does that make sense? It's something I came up with. It might not work at all, but do you have any thoughts?
So you're talking about different generations. Is a new generation defined as like a new time point? So like you'd make K children for when you're predicting for n+1, and then do it for n+2, etc.?
I think so if we have, like, if we're looking at the first generation and we look at 1-2K children, okay, each kth children will have a prediction from n+1 to n+m, and then that signal that you predicted will be compared to the sparse representation of the endpoints in S. And the goal is that by picking the, I assume that there are some weights, some random initialization associated with the forecasting of any kth child, that you could use or randomize in the next generation such that the signal approaches the sparse representation, the signal that you predict for the next m time points approach that of what is observed in the first n time points. So if we do 10 generations, we'd expect that the data points you predict in m will look more like what is in n as defined by the sparse dictionary. I appreciate the questions because it helps me like formalize it better.
So what are the applications of this? Like, you're trying to predict like anomaly detection, like abnormal heart rate or something?
I don't feel like that would be
when that would occur.
Yeah. So have you met Edward Kim?
I took a class from him,
Okay.
but I haven't conversed in depth with him personally.
He mentioned how he shared a project with me that he worked on at Villanova, where he looked at different models that could predict data points in time, and they were really good at predicting the next time point. But he observed that, you know, when you try to predict any more than just 1 or 2 time points, the errors are additive, so you kind of diverge from your signal. He said it was a low-hanging fruit because, you know, obviously if you can predict in the future for any time series data, you can use that for, you know, identifying whether a signal will be higher than what is expected to. So, for instance, on my co-op right now, one of the modalities we look at is called intracranial pressure, and that's like the pressure pressing against the brain underneath the skull. And doctors are obsessed with keeping that pressure below like 22. So if you can have some sort of confidence that that pressure is going to increase to above 22 within the next 40 minutes or within the next 10 minutes, that can tell the doctors a lot. Like, they should give them a drug to make it so that they can give them, like, I don't know the drug's names, but they can you know, establish like an intervention so that the patient won't, so that the patient has less of a risk of having elevated ICP. So, and this isn't limited to, you know, time series of things in the medical field. I think that this problem, or if this method works well, it could, you know, be applied to a lot of other things. It'd be better for more periodic signals that can actually have a sparse representation associated with it. Less so with things like stock prices, because those aren't so, you can't predict those too well.
Sure.
Yeah. Cool.
So is the sparse coding, that's just based on what you've observed, right? That's based on the endpoints. Mm-hmm. So if you make a sparse, I don't know if I'm using the right terminology here, but if you make the sparse coding from those endpoints, say you haven't observed anything abnormal in those endpoints, I feel like conceptually, if you were searching for the predictions that most closely match the sparse coding, you would be biasing your predictions towards what's normal.
Yeah, it's incredibly biased. And I don't know whether we'd want to predict something that, you know, it'd be hard to predict an anomaly if you haven't observed one.
Right.
I guess this project is just trying to, at least what we think is that this project should tackle just the idea of of forecasting a signal without having the time points,
Sure.
without having the predictions diverge. Yeah.
Okay.
Cool.
So are you thinking of picking individual children or taking like a weighted average, weighted sum of them? Sorry, I know I'm circling back to different topics here, but
it's okay. I didn't think of that.
Because I'm thinking if you started to observe a lot of the children that were heading towards abnormality, if you're taking like a weighted sum or something, then that would indicate like maybe there's something weird going on. Versus if you were just picking the ones that best fit like the previous signal, you might miss something going on.
Okay, so let's define another variable. Let's say we have like L generations. So you're talking about for like the L plus first generation, picking a weighted average of the K children that you have in the Lth generation. I don't know, because like if the weights, okay, so if the weights were based off the sparse representation, that would be a good idea. I'm just afraid that you might have so many, like when you first start, you might have so many signals that just like completely miss the signal. Those would have to go to 0, obviously. I don't know what would be better, actually, whether you do a weighted average of the best Z children in K, or you just take the best one.
You could do like a distance-based metric, like if you have a running average of the previous endpoints, like the further something is from that, this is just very basic, but the further the child is from the running average, the less it's weighted. Mm-hmm. But then as you start to see more and more children diverging from that weighted average, then eventually like the weights would allow that to show up in the forecast.
I think the weighted average would work better if we were picking the best child in K, but we're probably going to pick like the top. Most genetic algorithms, they pick like the top 5%, and then they use those to randomize it for the next generation. Yeah,
taking like top K, whatever.
Top.
And then taking the average of those or something.
Top alpha in K. We're running out of letters.
Yeah.
Cool. Okay. Yeah. Thank you for the questions. Yeah, and welcome. Is this your first time here?
Yeah, I've had schedule conflicts for the last several months, but
yeah, and we're happy to have you. I appreciate the questions because it's hard to explain this.
Yeah,
to new people sometimes. Not because of you, but because of me, because I end up rambling and all.
No, I know the feeling. Cool. Like you have ideas, but you don't know how to exactly articulate it.
Yeah, cool. So yeah, I think in talking, thank you, Cameron, that brings up a lot of different definitions. Like we defined the first n time points, the next m time points that we're trying to predict. It's multi-step, not single step. We're dealing with children in each generation, so we're dealing with K children, and we're dealing with L generations. Does anybody have any other ideas or thoughts? This is going to go right into some, hopefully just in the LaTeX document.
So I was just reading through like a few of the data sets which are publicly available. Mm-hmm. And I found like there are a lot of recent data sets, specifically for COVID patients. Mm-hmm. Because like we have seen that there has been like an effect on, heart strokes and stuff. So like as we can predict like how like the graph's gonna go, like seeing an instance of like the ECG point, if we like I don't know, I'll need to read a bit about it, but if we also merge a few more features with it, maybe we could create kind of like a detection model, how the risk of heart failure or any other stuff, specifically with COVID patients. It's like
that's very relevant.
Like like what I am thinking of is like as you go into some hospital and you're just admitted, you get your oxygen level checked, your heart rate checked, and you just get your ECG done. So with that ECG report combined with your other factors, you could maybe predict valuable information that how this patient is going to go, specifically in terms of heart.
Mm-hmm.
Maybe
So
that
you,
could be.
yeah, you bring up a couple important points. The first one being like the difference between like univariate and multivariate, like Alicia mentioned last week. And for right now, I mean, everyone wants to go to like a multivariate analysis where you take in multiple factors, like you mentioned, other things like EEG and heart rate and that kind of stuff. That's a more difficult project. Right now, we're looking at univariate, where you're only looking at it against time. This is how the signal deviates in time. And then the second point is, so it would only be clinically relevant if the next M time points were a lot. So if we can predict, instead of predicting, the next 2 or 1 time points with a relatively great degree of accuracy, we can predict the next 10. I mean, if we're dealing with something that's 256 hertz, like ECG, then that's not exactly helpful. It's not even a second to the future. So it depends on how well it works, right?
Like if we predict like just a few points, that it won't be useful, like specifically in a diagnostic setting.
Mm-hmm. Cool. So, okay, I'm gonna save this because we're gonna use this in my PowerPoint. I'm just gonna copy and paste it. I always think in PowerPoints. Before I leave here, does anybody else have any other questions? I mean, it'll come back. It's literally just gonna show it in PowerPoint instead. Cool. Desktop. Oh yes, and I was just starting up a LaTeX document that I'll share with everybody in the Slack channel.
I have a quick question. So this project, I remember in the Slack you sent like a conference. Like, are we get like? Is there like any like the single practice conference? Like, do you want to submit to that with this?
It'd be. It wasn't a goal of mine. I didn't think we'd have enough time to rush that, and I wouldn't want to rush a project like this. I don't want to rush this idea because I think that we can do a lot with this. I attended their conference last year, and it was like really good. It's definitely something that we could submit in a year to them, but depends on how far we get with all this.
That's understandable. 100%.
Yeah, so we'll call this figure 1.
But still, like what are we keeping the time frame for this project? Like
a term.
Okay, because
Yeah.
like if we go around till, like, if you're done with an abstract and everything till December, there are like a couple of conferences during that time.
Mm-hmm. Yeah, so plenty of opportunities.
Yeah.
Okay. So this is our highly scientific figure here, and we're going to start off with just defining some stuff. So we're going to say let S of t be our signal. And then we said time. And we're going to look at what k children in each L generation. So let k be the number of children in a given generation. L be the number of generations. Okay. Okay. And then what else we need to do is we need to say for each generation, for each kth generation, we are predicting okay, we are forming a sparse representation of the first n time points in SFT. Okay. So that sets up the signal, the independent variable, the number of children each generation, which I might move this later just to, actually, no, it's fine. So that's the number of children, it's the number of generations. And then we're looking at the kth generation. We're forming a sparse representation of the first n time points in SFT. And then, oh, actually, sorry. For each nth generation. In the nth generation, we're forming a sparse representation. Okay, and then what we want to, using the first, next, actually I want to keep that in here. Predict the next, then predict the next m time points for each kth child. Okay, and then each kth child will be associated with a random set of weights to predict. Sorry, I hear some feedback. That's fine. Okay. Yeah, so each kth child will be associated with n. So that's the thing common between all children in a given generation, is they all have the same n time points that they're basing their predictions off of. But I imagine that when you do time series forecasting, there's going to be some set of random weights that you can use and change and select, kind of in a Darwinism kind of fashion that allow you to pick the best ones. And there are, I mean, there's gradient descent, which is used in machine learning, but I'm pretty sure that those are used for when your the function you're trying to model is differentiable, but we would have to identify a function that we're trying to optimize, and I don't know whether that's exactly possible. That's a much more methodical way about finding some optimal set of weights or something like that, but I don't know if that's that's possible here. If it was, it'd be a lot quicker way to find what we're looking for. Okay.
Ethan, can I ask some questions?
Yeah, sure, go for it.
So what do we use to create the sparse coding? Is it like a neural network, or what is that process there?
Oh, okay. Have you done any sparse coding before or heard of it?
Mm-mm.
Okay. So sparse coding is an optimization problem that there are a lot of methods that do it, a lot of frameworks. So I'm not necessarily worried about, how we're going to do it, just that there exists a sparse coding, and sparse coding has been applied onto ECG before, but it hasn't been used in this way for as far as I know. So sparse coding attempts to solve this optimization problem where you're looking for a dictionary and a reconstruction image, to which this these two terms are at a minimum. This first term is the reconstruction error. So if you have a signal xi, you want to basically minimize the difference from the reconstructed image, which is just the dictionary you're building and some reconstructed image. So that this R of I can be thought of as an activity matrix. So it tells you the relative contributions of each dictionary element that would be used to reconstruct each x of I. And then this term is sparsity term. So by minimizing this, you're minimizing the amount of non-zero elements in each R of I. And then there are a lot of frameworks and a lot of algorithms that have been used to solve this problem. So for the sake of the project, I'm assuming that we can solve this optimization problem and get a dictionary D that we basically use something like this, or something similar to this to form an objective function for each like kth child in the nth generation.
So I think I'm confused. Are the children different sparse codings, or are the children different like forecasted time series?
Different forecasted time series.
Okay.
They would be compared to the same sparse children, the same sparse representation, because n is constant here.
So okay. So you're making a sparse coded n.
Yeah.
And then you have also sparse coded children, but those are the predicted time series for m.
Yeah, and you compare the sparse representation of m to that of n.
Okay.
And then using some objective function I haven't figured out yet, you'll predict the top 5% of k in L, and then you'll use that to generate the next k children in L+1.
Okay.
Okay, cool. Yeah, good question. I was also unsure with the whole sparse coding when I first saw it, and after digging into a bunch, I mean, there are plenty of frameworks that just solve it. So I think there might be some in SciPy. Actually, I'm not sure. I know Edward Kim uses a different library, and I know Osamu, who's probably not paying attention here, but I don't know what he uses.
Oh, I just made it with TensorFlow,
Okay.
but it's like a really basic one.
Yeah, so there's frameworks that can do it. Yeah, thanks for the question. Okay. Cameron, do you have another question?
I'm just trying to think through everything.
Yeah, okay, no worries.
Yeah.
Okay, me too. So yeah, for each else generation, we're forming a sparse representation of the first n time points in S of t, and then we predict the next m time points for each kth child. Okay, and then using the sparse representation, form or somehow score the predictions of the next m time points against the original application. And then let's just say let alpha be the percentage of children sent to the next generation. And then send the top alpha children to the then the top alpha children. Well, alpha would just be some like percentage. This would be like 5%. Then children to the L+1, L+ first generation. This would be so like this defines what I had in mind, and also what I've realized in talking to Cameron and other people who have questions. And you can kind of quickly see that this will just form the basis for an algorithm that we'll implement, where we want to score what's basically predicted, pick the best, and use that to predict the next generation. So in writing this, we come with some questions, some things that we haven't implemented and we really haven't talked about. So, like there's some questions we have. So So one might be, how do we find the sparse representation? How do we find? Answer that, we might use something simple in TensorFlow. I'm sure that Osamu, I know Professor Kim, he uses some other algorithm in his lab. We might compare different algorithms, see which ones work the best. Another is, sorry, I have a chat. Is there a heartbeat that we can compare to see the accuracy of it after using the algorithm? That's a good question. So Cameron mentioned earlier how there's like an inherent bias to what we include in our S of t in the n time points we use. So this diagram is relatively simple. I mean, it has 3 peaks. You use a lot more data than that to form a dictionary of features. And it'd be cool to cross-validate it against, you know, another person or some other type of random assortment of features from the same modality. But there is definitely ways that we can cross-validate our predictions to see whether it's whether it can be used. But yes, and that brings me to another question. So that even proceeds. How do we find this sparse representation? What data are we going to use? And Savek was very kind enough to, I don't know, kind of volunteer to help me do that, because we do need to find a data set, and I'd like to do that as quickly as possible. In winter term, this past year, we had a problem where we wanted to do stock predictions. We wanted to do you know, pattern consolidation, pattern classification, but we didn't have a good we didn't have a good data set to use, because people just apparently don't readily give it out to you. I mean, there are plenty of data sets online which had it on the day by day, but we wanted something that was a little more granular, that where the sampling rate was really a little higher. So yeah, so we'll find the data set, we'll find the sparse representation, and then how do we define our scoring function? Cameron, you mentioned some sort of distance-based approach, which is I think is good. But that's just another that this would serve as our objective function, or our loss function. That's because we're trying to minimize it. Or it depends how we define it. It could be objective or loss. It's just which direction the scoring function. Does anybody have any other questions that they thought of that will help us, you know, actually implement this? Because that's kind of something that I'd really love to do, because I'm kind of curious how it's going to work.
I was just wondering what process you use to actually generate the predictions.
Oh yes, okay. So yeah, okay. So Alicia, what have you used in the past? I know you've done a little bit of time series forecasting. What kind of models have you used?
Yeah. When I did it, I used convolutional neural networks for time series forecasting. I mainly did classification, so I use convolutional neural network. I use inception time, which is similar to convolutional neural network. There's just like an added module called inception module, and another one called echo state network, which uses reservoir computing, which that's similar to recurrent neural networks. So
Yeah.
like there are a lot of like machine learning algorithms and models you can use for forecasting. It just depends on like the data itself.
Yeah. And then another thing is, how do we ensure that all K children are different? Weights. I'm positive that there are weights associated with predicting any given kth child, but it's about, you know, ensuring that they're all different. Cool, awesome. this doesn't look like much, but I think it helped. Hopefully, it helped people understand it more. So, okay, I opened up. I have this right here, which is just a PDF that I have to clean. Sorry, a tech document I have to clean. And I want to share the link with everybody. And we'll just get some administrative stuff out of the way. So if I go onto our Slack channel, everyone's on Slack. Yes, I think. I go to Drexel AI. We'll create, do we have like a time series forecasting one yet? It's a big issue in.
Yeah, not yet. We didn't make a channel.
Okay. Time series. So it's kind of general. And then people can come in as they wish. I think you'll see it on the side like as a plus arrow and you can just join. So I'll just do project paper. That's all a tech document. And then the GitHub will be right here. And then, okay. So we need to think about what we're going to do here. So we'll go in this README, and we talked about some tasks we should do, right? So let's think about tasks. So the first task should be to find a data set. So Vivek, would you be comfortable taking that on?
Yeah.
Okay, cool.
I'm just looking through a few.
Yeah, no rush. I mean, we're just thinking about, you know, the project and who can do what and who wants to contribute.
Do you guys want specifically like what's the bioinformatics type data, like heart stuff, or do you care where the data falls?
No, I mean, it'd be really cool, in my opinion, if we, you know, there's different hyperparameters you can change that aren't necessarily related to the machine learning. It can be like the type of data we use. It can be, you know, if we pick different like bioinformatics modalities, you could apply the same algorithm. This algorithm is very generalizable over different time series. So if we looked at how well it worked on different data, I think that'd be pretty cool.
Okay.
I've never seen someone apply an algorithm on different modalities. Usually a paper presents an algorithm for a specific modality. Yeah. So yeah, I don't think it needs to necessarily be limited to biomedical signals.
I think you raise an interesting point because something like a heart rate would be pretty, what's the word you use? Like pretty regular, right? Mm-hmm. Something like COVID-19 infections, that number, like it's going to be increasing probably exponentially, right? You're not going to have a lot of ups and downs in that. So you could look at the, you know, how does it compare on different types of time series? Mm-hmm. Cool idea.
Yeah. Oh, you're talking about like a population model.
Yeah, you can do a search. Tons of people try to just predict like how many people are going to be infected, what's the death rate, things like that.
Yeah, I don't think this would go well. I don't think this would work well on a population model or an infection model. I just don't think it would work well because of the fact that you're looking at, unless you trained it on other population models, like where the end time points weren't coming from the previous, like the signal, it was coming from another signal. I don't know. Like you have a collection of samples that were like infection rate for other diseases in the history of time, and you trained it on that, and you try to predict because you know, if we're dealing with, I'm just trying to say, I think it would work the best for something that is regular, because if you have, I wish I had MS Paint on my computer. you have something like, if you have like something like this, it's a little sigmoidal, but where it like plateaus, you know,
Yeah.
it'd be difficult to predict like this, given this information in the past. Like if you only look up to like right here, I think it'd be pretty difficult to do that.
No, yeah, that makes sense.
Yeah, because you're basically comparing these predictions to the sparse representation, right? So it'd be trying to form a pattern according to what you've previously seen, and then scoring against it. So it'd be biased to, you know, the exponential.
Yeah.
So it would always
Yeah.
predict that you're gonna try to, you know, in the future. That is a good point though, but I think that like semi-regular or regular periodic physiological signals would work the best.
Also, there's thing that like most of like the COVID like prediction models have already been there, and like we'll be finishing up this like the whole project like in a couple of months. So we also need to think about like if the work we are doing should be like state of the art.
Yeah, like relevant, you know.
Yeah.
We'd want that to do better than models, right? And I'm sure that at least Professor Kim made it seem as though all people who've tried to do this have encountered the problem of, you know, additive error in the prediction. Okay, so then we need to, so we have the data set, then we can, you know, clean the data set. We could do some filtering if it's a waveform data, but I think we should stay away from something that's like too, just give me a second. I'd want to stay away from data like EEG, like for the machines the data that we use at my co-op come from machines that have like 256 hertz, and EEG is like pretty irregular. It's not, it takes a trained physician, like a neurosurgeon, to recognize patterns, and a lot of those patterns aren't exactly local. They stretch out for a long period of time. Well, for a long period of time beyond, you know, a couple hundred data points. So data set, and then what would be the next thing? What do you guys think? Data set. We'd want to implement the algorithmic framework. That would be just a very simple function that would do this, and to do this right here isn't too difficult, because at this point we're just assuming we have all the variables. We do want to, so that's like what you're doing over and over again. That's the genetic algorithm of it. Another point of that would be forming the sparse representation data. I might ask Osamu to do that because he's done it before. TensorFlow. How is that, Osamu, if you're around, how is that thing in TensorFlow different from what Professor Kim uses in another library?
It uses a GPU.
Oh.
Yeah.
Okay.
I think that's pretty much it.
And that makes it better?
It makes it faster. I don't know if the algorithm is as good.
Okay.
Yeah.
Okay. Thank you. I guess another task would be to design the objective function, loss function, depending on which way we choose to do it. We could start off with like a distance-based metric like Cameron mentioned, or we could, you know, try something else. Maybe like convolution metric. I don't know. And then there's obviously, you know, flesh out the paper. And then in the paper, we're going to have different sections that we're going to want to pay attention to. Like we have to come up with a title. We're going to have to work on the introduction, background. I will need help doing like I don't know as much as like maybe Alicia does with other papers that have tried to do this, or other, not necessarily famous, but other well-known methods that would go in the related work. So maybe let's also include that right here. So we're gonna look at related work, introduction. We're far from doing this, but like usually what I do is I work on the paper as I'm doing the project, so that we don't have to do it all at the last minute. It's good to have some stuff done during the coding portion of the research. Methods, and in the method section, really what you're going to see is just a more rigorously defined version of this. And then results and experiments. I'm including results and experiments because I mentioned to Cameron that there are other experiments that we could do, like doing it on different time series data to see how they compare, proving that it works, showing that it works well on, semi-periodic signals compared to evolution, like population and infection models. Because in a paper that we're actually taking, atrocious experiments. In a paper that we're taking to, or that YIT is presenting on at the end of this month at the International Joint Conference in Neural Networks, we talked about how well our method in that project, how that worked well in a certain circumstance, and then when it failed, and reviewers and judges loved that. So we'll include that in our experiments by showing that it works well in one setting but doesn't work well in another. And then the last one will be applications. And that basically will allow us to, I think that's the majority of the project right here, just some simple tasks. The hardest part, in my opinion, will just be implementing it. And then because we've been going through background last week, we talked about the algorithm today more rigorously and on a much higher level on Monday. I think the paper, on Monday, on the first week, we talked about it on a much higher level in the first wech. I think the paper will be relatively easy, given that everyone is up to speed with the idea behind the how it should work. So, okay, I didn't expect it to work like that. Depending on, that's why. There we go. Okay. So I'm going to work on this implementation right here. And then once we have the data, we'll send it around and see if we can, try to implement, oh, that's something else we need. Implement algorithm framework, form a sparse representation, implement our create time series forecasting model. It might be easy because I know there are plenty of time series forecasting models out there that have been researched and published. It'd be cool to just take one that has already been validated and then just use it in this algorithm, because we're not publishing a model. We're publishing an algorithm to find a good model. So this is very similar to what we did in fall term. In fall term, we applied binary search on neural network architecture search. The idea is that if you have an assumed distribution of some metric that you're trying to maximize, like accuracy in a neural network, you can, because you assume a distribution, you can search for the neural network size incredibly fast by using a binary search like method. So we weren't publishing a model that predicts on some data set really well. We were predicting on an algorithm to find the best model. And this is very similar to that because we're trying to use sparse coding and a genetic algorithm to find the best model, which is just a set of weights. So I think it's pretty similar. I think I like those more because sometimes it's difficult to actually find the best model because it's just a tuning of hyperparameters, and that takes a long time. In most cases, in other cases, it's the actual model or method you pick. But yeah, cool. Yeah, thank you guys. If you have any questions, I'll be here. And over the next week, I'll be posting in this channel, which I'll urge you to join because this is where I'll be talking about the data. We'll be discussing the objective or loss function. I'm sure Alicia will want to talk to us about the time series forecasting model we're either going to build ourselves or just take off the shelf and use. And when I say off the shelf, that would just be the model, and we'll train it on our own data that we have that we're trying to look for at this point. As for next week, we'll be talking again at 3, whatever that date will be. I don't know, in 7 days on the 13th. And we'll go over just updates. And if anybody has any questions, we'll talk about them there. But hopefully by next week, we'll have a little bit more of a foundation. And then we can get into more details about the code. But for now, I'm just happy that everyone's engaging and asking questions. This is actually the most amount of people we've had at a Drexel meeting for a while. So I'm pretty happy about that. Yeah, thank you for showing up. Hopefully everyone has a good day.
See ya.
See ya, Samu. Bye, Steven.
See ya.
See ya. Bye, Andy.
Ethan,
What's up?
what kind, like I was looking through data sets, you have worked with like the brain data, right?
Yeah.
So what I was thinking was like, because we do not need like a lot of modulations, but we need something which is consistent, right?
Yeah.
So like when there is like a tumor detection using the fMRI scans, like we pick certain voxels and see how the neuron function is going on, like depending upon the fMRI scan, and we get like it's not as like it's not 256 hertz as the EEG data, but it's kind of useful if we like.
You're talking MRI scans.
Yeah, it's MRI scans, but it's like volt signals, like blood oxygen level diffusion signal. So I think that is really cool too,
Yeah. Like I think it'd be. Sorry. So what does it look like? Is it one-dimensional data?
Wait, let me just show.
Is it semi-periodic? Like
yeah, it looks like ECG data.
Okay, what I have in mind, and the reason why I wanted to go with ECG is because of the fact that when you look at the data, you can tell it's following a very discrete pattern. And we don't want to necessarily get caught up in artifacts in the data. Like right here, it's very obvious that there's a pattern here. And I don't want to get caught up.
Share my screen?
Yeah. I don't want us to get caught up with artifacts. I just want us to show that we can, given a semi-periodic signal, we can predict it farther.
Can you see like the?
Yeah, I see. It's just, I'm worried that that's too irregular for us to start with.
Like,
Could you look for like an ECG signal?
ECG, okay.
Yeah. That's the heart. Like that.
Okay.
Yeah.
Okay. All right. So we need like a simpler kind of signal.
No, that's good. I think that's simple enough.
I'm Ethan.
Yes.
I have there's something I think I should show you that I've done that might help. I think
Okay.
I'm not sure. So I mean I don't know how this will apply because I've never done like AI stuff before, but I'm just going to show you. Okay. So okay, before I start, I'll tell you what it is.
Okay.
So the way it works is if you know what discrete
Yep.
Fourier transform, right? So basically, I set that up for something, for a sound wave, and what I managed to do is I managed to replicate that sound wave using discrete Fourier transform, and like so I save a wave file as my the Microsoft wave file, and then I actually read the bytes of the file like just hexadecimal bytes, and then what I do is I convert it into a just I guess an array that the computer can read. And then from there, I do the discrete Fourier transform on it. So I can then take out all the other sine waves. Because okay, so the way discrete Fourier transform works is that you have sine waves for each sound signal that creates sound signal. So there are like thousands of sine waves that create one specific sound signal. So if you have the periods set up the right way, it'll repeat itself. So how I think this could help is it could like we could use it to see the percent error or something like that, because it would always be the same if it's not changing at least.
Yeah. So that's good if the signal, if like each it's good if the period is like exact, because what you'll see with that error is that there is shift invariance. The data won't be it won't be time invariant, because if you were to just like, maybe I'm not understanding you correctly, but
so actually I think I know what you're saying. So the period so you can't have it slightly off, or else eventually it'll go away. So I've actually accounted for that. I think at least I think I know what you're saying. So I've accounted for that. So okay, here let me share my screen real quick.
Sure.
Okay, so if you can see this, so this is so what I did was it's a piano sound effect. So I actually imported it, like I imported the bytes, I undid it, and now I just repeated the sound, but using just many different sine waves, because that's how discrete Fourier transform works. So now if I right click, we're not going to see this, but it's going to save. So there's another window I have. So now it should save. It takes a little bit of time, like a few seconds. Okay, it's saved. So remember the shape of this, because I'm going to close it now. So you can, just remember, okay. Now, I'll open up Audacity. Okay. Import.
Okay, Ethan, I might head out. I have
that's
another
fine.
meeting,
Sure.
and I'll keep you updated on the data. Okay.
Sure. Thank you.
Okay.
Good day.
Cool. So see you later. Okay, so here. So you see that it looks about the same, right? So so this actually repeats. So as you can see it now separately. You can see like it repeats. So that's what I'm talking about. So I counted for that, I think, at least. So it does change a little bit after, but that's actually more so the way the sound wave is changing. It might not be perfectly exact for how it changes, but the actual it'll repeat. So it's never going to actually diverge. You know what I mean?
Yeah.
So it's repeated like I think 6 times here.
What would be cool is if you have your predicted and your actual like side by side, and then you compute the distance between them.
Exactly. That's exactly what I was thinking.
Yeah. So just if you do that, you might see that in some cases when you have very periodic signals, the shift isn't isn't there. But if you do have signals that have a little bit of shifts, like the difference, the time between each heartbeat isn't exact, and that'll show when you try to repeat signals like this.
Oh, well, yeah, that'll show. Like, obviously, like, yeah, if it's different, but it'll still repeat itself at least. But yeah, you'll be able to know it's not going to be exactly the same.
Yeah. No, good idea.
Yeah, thanks.
Definitely.
Yeah,
And
it's just something I've done. So
what's important when you do papers like these is you want to compare this to like a benchmark, a naive approach, or something that, something you could just do really quickly to see how well it would do. So maybe we could use this as a benchmark.
Yeah, you could. Yeah, I'd be willing to help you guys with that code.
Yeah.
I did this in Python, just so you know. So
Okay.
I don't know if that's compatible. It should be, but
Do you have this on GitHub?
no, I just have it on my computer, but I can move it.
Yeah. Could you put it on a GitHub repository and send it to the link in the time series chat?
Yeah, sure. But that might take a little time. But yeah, sure. No, I'll do that.
No worries. No rush. Yeah. We have till next week.
Okay. Also, if you want to hear the sound too, this is what the sound. It sounds like actually quite realistic. It's pretty similar. So.
Sure.
You hear that?
No, I didn't hear it.
Oh, let me reshare it again.
Share a sound.
Yeah. Yeah, I always forget to click that. Okay. So let me even actually, because sometimes it changes the wavelength a little bit, so it's a little higher or lower. So I'm just going to fix the pitch a little bit because I heard the pitch was off. Actually, no, it's actually the speed. So let's speed that up just so it's a little bit higher, so it's not so weird. Here. Oh, that's a little too much.
Yeah.
Okay. So you should hear it though, right? Get it?
Yeah.
Yeah. So that's this piano that I repeated with just individual sine waves.
Cool. Yeah. Cool. Thank you for showing me.
Yeah, you're welcome. So I thought that would be helpful. So okay. Cool. So and how are we gonna do this with the GitHub thing?
Just Google. If you never used GitHub before, there's
I haven't
plenty of
used
people.
it before.
Yeah. So just like there's YouTube videos. There's Google. Like creating a repository. Then you can just like set it up on so the idea is you like create something that's like on GitHub, and then you create something that's on your local machine, and you can push and pull between those two repos. And then you just send me the link to the one that's on GitHub.
Okay, cool. Thanks. Okay.
And what's your major? Are you CS?
Actually, I'm software engineering, which is pretty close.
Yeah, software engineering. Yeah, it's important that you learn how to use GitHub.
Yeah, I've definitely seen it, but I haven't ever actually used it.
Yeah, good opportunity.
Mm-hmm.
Cool.
Okay, cool. See you then.
Yeah, I'll see you.